Up until now, you've been working with the derivative. We've called the derivative a variety of different things. We've called it f prime, we've called it y prime, we've called it dy dx. That's dy over dx. Now dy dx is a noun. That is the derivative function, dy over dx. This is going to be the first time where we separate the dy and the dx, and we look at dy all by itself, and we look at dx all by itself. And what is the meaning of that? You know the meaning of dy dx. It is a function. It's a derivative. Its job is to give me slopes of tangent lines. You also know what d over dx, that's a verb, an action verb. d dx, that's an action verb to take the derivative with respect to x. But what's dx mean all by itself? What does dy mean all by itself? And that's what we're going to learn in this section 3.9 about differentials. Now, the first thing we're going to do with differentials is we're going to talk about using a tangent line as an approximation of an original function. Perhaps you've got a function that's complicated, it's difficult, and it's got a lot of computational work that needs to be done, many terms, high powers of x, trig, and there's a whole bunch of stuff in there. Big, huge function. Well, if we were able to approximate that function with a line, in fact, it would be the tangent line would be the best approximation in a certain region of our curve. Lines are much easier to calculate the y values, so a linear approximation is so much easier to compute, and it's probably going to be pretty good within the region of where you've made that approximation. So that's why we do it, and I want to show you how we do it. The way we do this, and I'll use the example in the book. It's a good example. It's a trig function. Now, it's not a very complicated trig function, but trig functions do require some computational effort to compute. And this particular trig function is just the sine curve, and it's been shifted up by 1 unit. Now, the sine curve has a period of 2 pi. Right in the middle, that's pi. In the middle here, that's pi over 2, and in the middle over here is 3 pi over 2. Normally, the sine curve goes up to 1 and down to -1, but what happened here was it got shifted up by 1 unit. So instead of being down here at 0, we're up here at 1. Over here, instead of peaking at 1, we're up to 2. Now we're back down to here. And then it dips all the way down to here. And then finally, right back to the middle of 1. Now, this is what the sine curve would have looked like if this was the x-axis, right? So we're going to sketch it. It goes up here, curls around that corner, sketch it around here, comes down through here, and then finally goes here. And, of course, it does go on forever and ever, right? So what if I tried to do something like this? If I were to zoom in over here at the region near x equals 0 and said, instead of using the sine function, instead I'm going to use a tangent line approximation. And the way to do that is to draw a tangent line right here. Now, the tangent line is going to skim across this curve just like so. It's balanced up right there at x equals 0. And take a look at the tangent line and the trig function in this region right here. They're basically identical. So what's really nice about approximating a function with a line is that we can actually, in a sense, cheat. We can use the line, the function or equation of the line, to literally approximate the more complicated function. So let's find this tangent line. Now, that's nothing new to us. Finding the equation of a tangent line, shouldn't be something new. So let's go ahead and do that. And I want to show you that in the region near x equals 0, that the tangent line and our original complicated trig function are basically saying the same thing, same outputs coming out. How do we do this, guys? Well, we all know a point on our curve and our line. That's 0, 1. That's a given. But what is the slope of this line? It's a tangent line. We need f prime. Well, the derivative is cosine. And that's not the slope of the tangent line, right? We need to sample the derivative where we are, which is x equals 0. And now I have the numerical slope of my tangent line. That's 1. Now, if you know a point on a line, and you know a slope on a line, we've got this magic formula called point-slope form that will tell us exactly the equation of that line. So y minus y1 is slope times x minus x1. Y minus 1 equals x, or y equals x plus 1. Now, the original function was this. So what I want to effectively do here is I want to prove to you that the line and the function are basically identical as long as you stay close to x equals 0. So let's make a table. And in this table, let's put the function right here. And by the way, we will be evaluating everything in radians when we do use that sine function. Let's put the linear approximation, which is right here. And you'll see we don't even need a calculator to compute that. And what I'll do is let's stay close. In fact, I think we all know that at x equals 0, the curve shares the same exact point with the line. It's got to, because the line and the curve touch there. That is a point of tangency. But let's stray a little bit. Not too far. 0.01. Well, I don't think we have any trouble calculating this. That's 1.01. But this, if you plug 0.01 into the sine in radians and add 1 to it, this is what comes out. 1.099999. Wow, is that close to the linear approximation. Let's go on to the left side at minus 0.01. Now, if you use the line, it's pretty easy to do. We don't really have to get a calculator out. It's going to be 0.99 exactly. But if you feed this into the trig function, what do you get out of it? You get 0.99 and how many zeros? 4 zeros and a little 2 at the end. So is the function the same as the line? No, they're slightly different. Are they close? Incredibly close. In fact, we're within, seems to be about 6 decimal places right now. So that's pretty good. I mean, that's really good. But what happens when you stray a little further away? You go over here to 0.5. Well, we already know the answer to this, right? But what is 1 plus sine of 0.5 radians? We're starting to lose that accuracy. We're starting to drift away from this line. And we certainly expected that. Now, if we go back too far, now we know what this would be, right? That's 0.5. And what is this going to be if we were to plug that into the sine function? We get 0.521. So we've lost that incredible accuracy. There's an amazing amount of accuracy as long as you stay really, really close. So that's how linear approximations work. You find the equation of the tangent line. Boy, that's nothing new. And we plug x values that are really, really close to the point of tangency, and they're practically the same. Now, if I were using a small device that was trying to compute something, and I was using a microprocessor, and I had a really complicated function that was computing something, whatever it is, volume or, temperature, or whatever it's calculating, and it's got some incredibly complicated engineering formula that somebody came up with and figured out. Wouldn't it be a lot easier to use a line or a linear approximation? Look how easy it is to calculate, and it would save the computer a tremendous amount of processing cycles or time. Now, as long as you stay super close to your point of tangency, the accuracy is really good enough. It's within 6 decimal places. That's plenty good. So now, let's take a look a little further. What is a differential? Now, if we draw a curve, f of x, we draw our curve, f of x, and we place a point right here, and we'll call that the point of tangency. You know, we'll draw a nice tangent line up against that. We balance it up as well as we can. Now, the slope of this tangent line is represented by dy over dx. And isn't that interesting that it looks like a fraction? That's rise over run. That will play a role in just a little bit. But if I were to go down here and point to this x value and call that c, and then I strayed from this point. Now, we don't want to stray too far, maybe this far. The distance from this point in x to that point in x we will refer to as delta x. So this will be c plus delta x. We've done that before. Now, the real world is on the curve. That's where the real answer lies. And if you look here, we've got y values to look at. Right here, this would be the f of c. And right here, shooting across to our y-axis, we've got the f of c plus delta x. We've done that before too. But let's make it even easier than that. Let's just call it delta y. Let's call this delta x. So as you changed x, you got a change in y. We refer to that as delta y. But what if we cheated? And instead of using the curve, we use this tangent line approximation. And that would be right here. What kind of changes did we get? Well, you'll notice that we got the same precise exact change as we did below, but we got a different change in y right here. And it's different than the actual delta y. And what are these two changes? Well, dy dx is rise over run on a line. dy dx represents the slope. So this is the rise. And this distance is referred to as dy, all by itself. This distance is the run. Well, the run is referred to as dx, all by itself. So the first thing we realize is that delta x, the real change in x, is equal to dx. They're really one and the same. Delta y, the real change in y, that's delta y. Well, dy is not exactly delta y, but at least they're somewhat close. So what are these things, differentials? What does dx and dy mean when they're all alone like this? Dx means a little change in x, and in fact, it's exactly the same as delta x. Dx and delta x are the same thing. Dy represents a little change in y, which is not the same as delta y. Delta y is the real exact change in y. If you were to really use the function, you would get delta y. Dy is when we're cheating a little bit and we're using the tangent line approximation. So dy is not exactly right, but we're going to say close enough. It's approximately equal. So what we can do with differentials, because delta y is so close to dy, is that we can use dy instead of delta y. And what would the benefit of that be? It's less computationally intensive by quite a bit to find that difference. Now I'm going to show you how to use this in a real-world application, and one of the places that we do use this is in error propagation. When I say error propagation, what I mean by that is when you take a measurement like, let's say it's a sphere. In this case, we're measuring the radius of a ball bearing. So you take a sphere ball bearing, you're working at some engineering company, and they say, all right, I want you to measure the radius of the ball bearing. So you take an instrument and you measure it. Now, every measurement has a level of accuracy associated with it. So when you get that your ball bearing is, whatever, 5 millimeters, is it exactly 5 millimeters? No, of course not. It's 5 millimeters plus or minus whatever the accuracy of the instrument is, plus or minus maybe 0.01 millimeters, something like that. So how does that affect the calculation of the sphere's volume? Is the volume off by 0.01? No, the volume's off by something else. So what I want to do is I want to show you how to use differentials to approximate the error that propagates into some calculation. And by doing so, you save yourself a tremendous amount of work. So let me show you how to do this using calculus, and then I'll show you how to do it without using calculus. And without using calculus, we're going to have to be doing much more in terms of operations. So let's get started. So let's look at a problem where we're measuring the radius of a ball bearing. So here's a sphere, and we're measuring its radius. So I guess we can use a caliper, and a caliper will actually do this measurement for me and get me the radius of that ball bearing. And let's say we measured the radius. Well, certainly you'd measure the diameter, and then you divide by 2. So the radius we measured to be 0.7 inches. Now, if you look at your caliper, it will always tell you the accuracy. This is a measuring tool that we would use in like a machine shop, for example. It would say, well, the true change or error in that is, in this case, plus or minus 0.01 inches. So really, if you think about it, I don't really know the radius. All I know is that the radius somewhere between 0.71 inches and 0.69 inches. So there's some ambiguity here into what the radius truly is. The volume of a sphere is 4/3 pi r cubed. So at the 0.7, we can calculate that it's 4/3 pi r cubed. So let me do that calculation for you here and find out what the volume of this sphere actually is. 4/3 multiplied by pi multiplied by 0.7 cubed. So I'm picking up a volume that is 1.437 cubic inches. Now, I've decided to actually do this without calculus first. And what I'm going to do is say, well, is that really the volume that I would then tell my boss, hey, the volume of the ball bearing is 1.4. He'll say, yeah, that's true, but I need to know how big it possibly could be and how small it possibly could be as well. So it's 1.437, it's plus or minus something. There's got to be a range of volumes because you have a range of radii. So you would say that's true at 0.7 inches, that's what I calculate, but it's very likely because of the error in this instrument, it could be as small as 0.69, in which case I would recalculate my volume as this. So let's do that calculation. That's going to be 4/3 multiplied by pi times 0.69 cubed. Now, on the small end, we get a volume that's 1.376 cubic inches. And don't forget, it's possible that it's 0.71. So we have to look at that one too. And that would be 4/3 pi 0.71. So because of the ambiguity, you're not really sure what volume is. Times pi times 0.71 cubed. So on the high end, it's 1.499 cubic inches. Now, the final result I'm going to deliver to my boss is that the volume of the sphere of the ball bearing is 1.437 plus or minus some number. So what is that number? So I want to find out what that plus or minus is on the volume. It's not going to be 0.01. So if I take 1.499 cubic inches and I subtract 1.437 cubic inches, let me see what we get from that. Minus 1.437, we get 0.0622 cubic inches, and that was an overshoot in volume, because this is the big volume here. If I were to take the small volume, 1.437 cubic inches, and subtract, take the small volume, that would be 1.376 cubic inches, and subtract the volume at 0.7, then what do we get in that case on the low side? 1.437, and I'm picking up a negative 0.061 cubic inches. So this is what I would tell my boss. The volume of the ball bearing is the 1.437 figure that we came up with by simply calculating 4/3 pi r cubed. Plus or minus, now, hey, if you want to encompass both of these, you have to take the bigger number. And maybe we'll go just to that number of decimal places. So you can tell with your boss with confidence that the volume is this, plus or minus about 0.06. I know we kind of went too much on the low side, but if you're only going to provide one number, then you need to pick the bigger of these two numbers. None of what I just showed you is what you're going to do, because none of that requires calculus. So let me say that again, because I see a lot of people doing what I just did because that's what was demonstrated. I don't want you to do any of that. That doesn't require calculus, and in fact, that answer is better in a sense than the answer I'm about to come up with because it's exact. We calculated the volume exactly 3 times. But think of how many operations you did, mathematical operations. We had 3 volume calculations, that's 3. We did 2 subtractions, and then we compared those 2 numbers to pick the big one. So in a sense, we did 6 operations to finally come down to this answer right here. 6 operations to get there. What if I said we could do this in, 2 operations? Now, we got to calculate the volume at 0.7. I mean, that operation, I got to get that benchmark of where we are. But what if I said I could get the 0.06 number in 1 step? That saves me 5 steps, okay? So how do we do that? What this is volume. What this is the delta V. This is the actual real change in volume. That's the real change in volume. We calculated that very carefully, and we picked the higher number. What this is radius. And delta R is the potential change in volume because of the error of the instrument. It could be plus 0.01, it could be minus 0.01. Now, if you remember from your tangent line approximations, in this case, the R is like our X, is the independent variable, and it turns out that dr and delta R, the same thing. Same exact thing. But it turns out that dV will only be approximately equal to the actual delta V, which, if we remember, is about 0.06. So what if we could get delta V through an approximation, which would be dV, and we nailed that 0.06 in one simple step? Well, here's how we do it. If you remember, the volume formula is 4/3 pi r cubed. So where do we get dV from? There's no derivative there. We need a derivative. And we know how to take the derivative. So let's call it for what it is. It's one of these derivatives. We normally put the dependent variable like y on top. We normally put the independent variable like r on the bottom. And you just go ahead and take the derivative. So 4/3 pi along for the ride. R cubed becomes 3r squared, cancel. And so dv dr is equal to 4 pi r squared. Nothing new. We've done those before. How do we separate dv and dr from each other? Well, I want you to imagine that dv dr is one solid unit. It's a noun. It is the derivative. But I also want you to imagine that you could effectively move the dr to the other side by multiplying both sides by dr. Now, technically, it's not like that, but it does certainly work that the dr would cancel and you would actually get dv all by itself. Now, remember, dv is approximately what we're really seeking, which is delta v, because we got to tell our boss how accurate the volume calculation is. That would be delta v. dv will stand in for that. And it will be an approximate value. It won't be exact because it's using a tangent line. And we saw that tangent lines can only approximate. They won't be exactly the same. Well, let's see if this works. Okay, talking to my boss here, and I'm telling him that the possible error in volume is approximately equal to dv, which is equal to 4 pi r squared, which is 0.7 inches squared, times dr. What's dr again? Oh, that's right. dr and delta r is the change in r, the real change in r. And these are exactly equal to each other. So that's 0.01 inches, or plus or minus if you like. Okay, let's see if this worked. So now, if we go to the calculator here and we type in 4 pi times 0.7 squared, and then multiply by 0.01, look at that number, 0.0615. I'll round that to 0.062. So delta V, which is approximately dV, which is 0.062, and we got that in one step. So therein lies the power of differentials. We're able to do this thing called error propagation with one simple step. To get that 0.062 the other way, 1, 2, 3 function evaluations, 1, 2 subtractions, and then 1 comparison. That's 6 things to do. Instead, one thing, the derivative, split the derivative, and then you plug all the information that you have. We had dr, that's delta r, 0.01. We had r, and we calculated dv, which is approximately delta v. In fact, boy, it's pretty close. It's within 3 decimal places here. It's pretty good. So that's certainly one thing that we like to do with differentials. Here's something else that we could do effectively with differentials. Let's approximate a function value. Now, what if I asked you to take the square root of 16 and a half? I know you'd all say that it's approximately 4, but can you do better than that without a calculator? And the answer is not really. You could sort of guess, and then you'd square it. You have to. I'm saying without a calculator, can you give me a really good approximation of the square root of 16.5? There is a way to do this, and the way to do this is to use differentials. Now, the function we seem to be using today is square root of x. I understand that. And what we're really doing is this. We're doing the f of 16 and a half. So in a sense, this can be your x, and you're just going a little distance away from it. So this is some y value, y2. Now, if you just go ahead and do the f of 16, you're getting some other y value, y1. Now, what's the difference between these two numbers? The difference between those two numbers we refer to as delta y. It's the old delta y that came back. So I think what I'd like to do here, because I know the answer here, I think we all do. So the 4 is already there. We got the f of 16, the square root of 16 is 4, but what's delta y? 4 point what? Now, without a calculator, I'm going to have a hard time computing delta y, but what if we estimate delta y with dy? So, y is the square root of x. Y is x to the 1/2 power. So let's do this. Let's do dy dx. This is the regular derivative like we've been doing all along. And to do that, the 1/2 will drop down and you'll deduct 1 from the exponent. So basically, it looks something like this. 1 over 2 square roots of x. What do we do in this chapter? The chapter about differentials, we love to separate this noun into two pieces. We move the dx to the other side. You can almost imagine multiplying both sides by dx. And you end up with the new equation, which has differentials and not just dy dx. So it looks like this. Now remember, think about what we're trying to do here. Come on back here. Calculus is not needed up here. This is the f of 16 plus 1/2, which would get me the answer I'm looking for. This is the f of 16, which is easy, is 4. Delta x is how far we strayed away from our x value. And when I compute these two, the change in y is delta y. So here's what we're going to do. Let's use dy to approximate delta y. Now, what is x? Well, it says right here, x is 16. So dy will be equal to 1 over 2. It says right here, x is 16, square root of 16. But the big question is, what is dx? Well, we talked about that earlier. Dx and delta x, luckily, are the same thing. So what is this dy that is approximately delta y? Dy is 1 over 2 times 4 times 1/2. 1/16. So, delta y is 1/16. These two will be off by 1/16. So what does that tell us? So we already had the 4 part, and now we know how far off they were by 1/16. 4 and 1/16. Let's see how good this was. So what is the actual square root of 16 and 1/2? Well, 4 and 1/16 is 4.0625. And that's our approximation of the square root of 16.5. But what is the square root of 16.5? Run that through your calculator, and you will find that it's actually 4.0620. Pretty shocking. We were able to compute the square root of 16 and 1/2 without really touching a calculator. 4.062 is pretty good. So again, when you're looking for changes in y and you don't want to touch the original function, what we do is we use the derivative. We actually calculate dy. dy and delta y are almost the same, not quite. dx and delta x are identical, remember that. So when you see a delta x, you really do have dx exactly. And x is something will be provided. In this case, x was just 4. I'm sorry, 16. So x was 16. So it turned out that the dy formulation had a nice square root of 16 that didn't require a calculator, and I was able to calculate dy pretty effectively. Dy approximately equal to the delta y, the real change that deviated from the number 4, which was the primary portion of the answer. So I do encourage you to experiment with differentials. And remember, take a normal derivative. Let's start with that. dy dx equals, figure it out, dv dr, whatever that is, figure it out, and then break it off, take the bottom and move it over to the other side. And now they have meanings. So dy is a little change in y, dx is a little change in x. That's what those mean when they're all by themselves. Thanks very much. Work on that homework. Do let me know if you have questions. Thanks.